Okay, good. So sorry for the interruption. So we are back again, and let's remind ourselves of what we were trying to do. So last time around, we spoke about trying to define two-dimensional CFTs on T2, and what we were saying is that this is required. We tried to motivate it from the point of view of string theory. There we were showing you these these string tree-level amplitudes, and these tree-level amplitudes are essentially equivalent to inserting four operators on the sphere. So these are the tree-level amplitudes. Obviously, you cannot stop at tree-level amplitudes, and you also want things at 1 loops and 2 loops and so on and so forth. So you have to define CFTs in higher dimensional, higher genus Riemann surfaces. For example, you need to, for 1 loop amplitudes, you need to define them on this, donut shaped object, which is a torus, and which I'll also be referring to as T2. And so that's what we were at. Okay, so that's what we wanted to do. And so the thing that I tried to drive on last time around, what is the sort of simplest way of trying to do this? Simplest way of trying to move, trying to move to this T2 is first by looking at the plane and going to the cylinder, and then identifying two ends of the cylinder. So these were more than so on. So which we so the idea essentially was that you can think of this. It's a useful way to see, useful way to visualize on the cylinder by looking at this particular sort of identifications on the plane. So for that, what we did is we sort of latticized the plane, and this fundamental domain was given by this particular cell, and you saw that these identifications were omega is omega plus m alpha 1 plus n alpha 2. That was that, and where these alpha 1 alpha 2 are sort of complex numbers that spans a lattice, and as I said, the smallest cell is called the fundamental domain. So the quantity that describes the shape of this this T2 is what is called a modular parameter. We will name it tau, and this is going to be the ratio of alpha 2 over alpha 1. And we saw that the thing that keeps this the same, the sort of transformations that acts as an isometric group on this on T2 is something that also takes to tau takes tau to a tau plus b by c tau plus d, where a, b, c, d are integers. And also the fact that the same will also be true if you had minus a's and minus b's, means that you have to mod out by z2. All right, so there were these particular transformations which actually generated the group. These were called D transformations and U transformations, or equivalently, you could have T transformations and S transformations, where S takes tau going to minus 1 over tau. These are things that actually these are called the T and S transformations. These are going to be the ones that generate the group. For more on this, I advised you to look at the yellow book and look at the problem 10.2. Okay, so chapter 10, problem number 2 is something that I would like you guys to do. So have a look at that. All right. All right, so now the focus of the whole thing is going to be on partition functions in a CFT. So in the usual StatMech, this is a sum over all possible configuration, and it's weighted by this Boltzmann weight of exponential minus beta h. There's something similar, which this is the same as this is a generating functional in a field theory. And as you know that you can deduce thermodynamic expressions from a Euclidean CFT by looking at the erstwhile time direction and I mean identifying that on a circle of radius beta, where beta is equal to 1 over t. Now let's do this on our I mean t2, and we are going to be choosing real omega to be spatial and imaginary omega to be the time direction. Once we do that, so the notice what happens is that if you start off here and you just make a time translation, you don't end up in the same lattice. In order to get to the same lattice, you also have to have a space, I mean spatial sort of translation. So that's what describes in a sense a closed loop for you. Okay. So then, so what you need to do is, keeping this in mind, you need to define the partition function of a CFT as the trace over, trace over all the states of, of the Hilbert space, and these are sort of weighted by these factors. Okay. So what does this mean? So you take a state which is labeled by maybe I, and you do this e to the stuff and I again. Okay, so that's what this means. So that's the thing. So H is the Hamiltonian, P is the momentum, and the traces over all states of the Hilbert space. Now we want to figure out what H and P are in our case, and that's something that we did. And what happens is H cylinder is just given by L naught plus L naught bar, and P cylinder is L naught minus L naught bar. These are things that you would again expect. But remember, these are expressions on the cylinder. So what has to happen is that these guys, when you write it down in terms of just L naughts on the plane, there is a central charge shift to L naught and L naught bars. Okay. So you have to, partition function in the CFT defined on a torus with a modular parameter tau is then given by this object that you have out here. Okay, q to the L naught minus c over 24, q bar to the L naught bar minus c bar over 24, where q is given by 2 pi I tau. Very good. So now the point is, since SL2Z mod Z2 transformations of tau do not change this T2, what is going to happen is that the CFT, and in particular the partition function, will have to be invariant under this this sort of modular group. Okay. Now this is going to, we will see in this lecture, the thing that we have remaining today, that this is going to constrain the way you can put chiral and anti-chiral fields in this CFT. Remember, this is a feature that was not there when you are trying to do things on the plane. When you're trying to do things on the plane, you just separate out left moving sectors and the right moving sectors, and at the end of the day, you're saying, okay, all right, we just bring them together in an equivalent way. Here, since you have things which are moving on this donut shaped object, there was going to be some some sort of restrictions on what can happen. For example, I don't know if you'll get to that. For example, there will be restrictions on what for example, the central charges, what C minus C bar could be, just arising from demanding sort of modular invariance. We will see if we can do a little bit of that, but today what I want to do is I want to show you examples. Okay, so the examples we will start off with will at first be the example that you have looked at in some detail, just from the point of view of a free boson. Also, when we were doing string theory, we sort of repeatedly went back to this. So let's look at the example of the free boson. Okay, I'm going to be so For this lecture, most of this lecture, I will be following Blumenhagen and Plushen. So if there are if there's some things that I go over too fast, you can go back and have a look at that. Near the end of the lecture, I do something else, but I don't know if you'll be able to get to the end, given that it's already 3:20. But all right. So far, before I move on, any questions that are urgent? That was a very quick recap of what we tried to do last time. Okay, so if not, let's try to understand this partition function business a little bit more. Okay. So what we will do is we will start off with our free boson. Remember that you can write down the modes of the energy momentum tensor in terms of JZs. So JZ is equivalent. So this is J, what I write as JZ out here is equivalent to what we called alpha. JZ is equivalent to alpha Z, yeah, if you wish. I mean from earlier. Okay, so these are like the alpha knots, but let's stick to this for the moment. Okay, so JZ is I del x, where x is the scalar that we have. So L naught, as you have seen before, can be decomposed into J naught squared and J minus KJK. When we are looking at the ground state, so J n acting on 0 will be equal to 0 for n which is greater than -1. So that's what we are going to do. And so the states of the Hilbert space will have the form, I'll call a state this n1, n2, n3, when I have J minus 1 whole to the n1, J minus 2 whole to the n2, J minus 3 whole to the n3, and so on, acting on the ground state. This gives you the number n1, and this gives you n2 and n3, and so on and so forth. So remember that if you were to write down the algebra of the J's, then Jn with Jm gives you m times delta n plus m0. Remember that if you were to get to the harmonic oscillator algebra, you need to get some m's and n's. So you can get to the harmonic oscillator algebra am by defining am as well. Okay, Jm by root m. Okay, but okay, so we're not interested in that at the moment. What are we doing? We want to find this out. And at the end of the day, what I really want to get at is what is the action of L naught acting on this state. For that, what we need to do is we need to look at the action of J minus KJK and this J minus K whole to the NK. So if you do this, and if you say now act this L naught on these things with all of these n's, so you have the L naught which sits here, and there are all of these guys which would sit here, and you have to get to this, right? So all you do is sort of flip things around by this algebra, and keep in mind that Jn for n greater than -1 is going to give you 0. Okay, so once you do that and you plug things in, what you're going to get is the summation. So there's a sum, and so at the end of the day, what you're going to get, this is just straightforward algebra that you can do. You're going to get nk into k multiplying this state, and you need to sum over all the k's which are greater than or equal to 1. Just remember that J naught acting on the ground state is also going to give you 0. So that is why you don't get anything from the first term. This is going to change when we look at a little more, uh, more interesting examples a little later. So what do you want to do? We want to find out z. We want to find out z, which is trace of e to the minus beta h plus, sorry, whatever. So z is trace of e to the minus beta h plus something, whatever, xi p if you wish. Xi is not a good thing to write down. And this, as we saw, was trace of q to the L naught minus c over 24. And I'll drop the q bar piece for now. Okay. So let's do this. What does trace mean? Trace means that you have to sum over all the states in your Hilbert space. So the arbitrary states in your Hilbert space, as I said, are given by this object here, all of these. This is an arbitrary state in the Hilbert space, okay? So what you want to do is you want to take this guy. So what have I done? I have just written down, I've just expanded the exponential, and I have taken the trace over the state n1, n2, dot, dot. And the sum means that we are doing the thing over all the states of the theory. Okay. See that I have chosen. So it's it's a free boson, right? The central charge of the free boson, which is something that we have had before. Central charge is c equal to 1. So I have actually factored out this piece of q to the minus 1 over 24 outside. And this is the object that we are left with in the inside. All right. Very good. Now for the fact, now you use the fact that L naught acting on these states give you sum over k and k. So this is what I have done. I have a sum over k and k here, and this will be raised to the power p. Okay, and there's a sum over p as well. Now, what is this? So you can resum this again, right? You can resum this, and this is again an exponential. So once you do the exponential, and now I have written this out explicitly. So this is q to the 1 and 1 into 2 and 2 into 3 and 3, 4 and 4, and so on and so forth. So you write down this object, and you can take this outside now. And what we are going to do is that we are going to assume that you can also show this, that these are also sort of normalized to 1. Okay, so n1 n2 with n1 n2 dot dot, that will be equal to 1. So now what are we left with? We are left with all of these q's here. Whole to the power n1, whole to the 2n2, 3n3, and so on. And there's a sum over all of these n's, and there's a 1 over, q to the power 1 minus 1 over 24 sitting outside. So this is a sum, okay? And you can do this sum, and the thing that you end up with is this infinite. So this, as you again know well, if you're going to sum this up, this is going to be 1 over 1. 1 minus q to the k. Now there's a product in front of this as well. Okay, this particular function is what is called the Dedekind eta function. So at the end of the day, when the dust, when you have gone through all of these steps, this particular thing, q. So this also includes the factor of 1/4 in front. So eta of tau is given by function like this. So this is as I said, the Dedekind eta function. So now, so we have just looked at the left moving sector. We also need to get the right moving sector, which which yields a similar answer. So what we are going to do is, so the answer at the end of the day, what we find is that the partition function of this boson is just 1 over modulus of eta tau the whole squared. All right. So that was nice. That was quick and easy. Now, the partition function has to actually be invariant under modular transformations. You would have thought by doing this we will get something which holds, right? If you look at the, so just demanding modular invariance can be just brought down to demanding invariance under TNS. Okay. So it suffices to check that Z is actually invariant under S and T. Now under T transformations, Q goes to Q e to the 2 pi I times Q. Remember, tau goes to tau plus 1, and Q is e to the 2 pi I tau. So that's that. Now you can now this is something that you can easily do. You can see that if you do this on the eta function, if you take eta to eta plus 1, eta to eta tau to eta tau plus 1, then there is this extra phase that you're going to get. Okay, so as it stands, the modular this is actually so this function eta is not invariant. Okay, so it's not invariant under the T transformations. You can also find out what the S transformation is, and then what you're going to get is you're going to get this factor in front. There's going to be a minus I over tau in square root of this in front. So it's obvious that if you have something like this, and if you have this particular transformation, then this Z prime is not going to be invariant, right? Because there is going to be an extra factor which comes from here, which will not go off. So it's obvious that the free boson partition function that we have derived is not, it's not modular invariant. In particular, if you're doing the S transformation, then it goes to, there is an extra factor of 1 over mod tau. Now you can refine this and you can define a new partition function. And so what is actually happening is that the partition function is this. It is the trace of the things that you saw, but we didn't necessarily give the proportionality factor in front. Okay, and so you can actually see that this is going to be something which is going to be invariant. Okay, so this is by demanding the fact that our theory is going to be modular invariant, or our partition function is modular invariant, you got something which is this form out here. Now this has more, this has a deeper, string theoretic meaning than I can go into right away. But you can also derive this form from a more, this may seem a little, back of the hand to you, but you can actually derive this through a more sort of rigorous way by looking at path integrals. And for those of you who are interested, again, I recommend that you look at the big fat book. So maybe let me just write down more details. in the book by D. Francesco. But at least I wanted to give you a flavor of what is happening here, and you see that you need to be you need to make sure that your partition function is actually invariant, okay? And sometimes you'll get some extra pieces which you need to actually put into the game. Okay, very good. So this was what happened for the partition function for a free boson, and now let us do a few more tricks with it. Okay, so now let's sort of look at this free boson on a circle. So by a circle, what do I mean? So I am going to identify this field X with X plus 2 pi Rn. Okay. Now these jz and j bar z bar will again have these expansions, as you know. And if you write this write the x's in terms of j's, this is again something that you know from before. You can expand this out in this form. So you can one way to check this is that you know that del bar of x is equal to 0 is your equation of motion. If you plug this into the equation of motion, you will see that that particular thing goes through. Very good. So this is our mode expansion, which is 6.26. This is also should be familiar for from the string theory point of view. We still are working on Z and Z bar though. Now remember that if you are to rotate the plane, the complex plane by 2 pi, x should be invariant, but it should be invariant up to these particular identifications. Okay, so so z going to e to the 2 pi I z. If you do that, then x should go to itself up to this extra 2 pi Rn pieces. So if you now plug this back into my equation here, if you plug this back into 6.26, then what we will find is that you can look at j naught minus j naught bar, and that has to be equal to r into n. Okay. So what happens then? So j naught minus j naught bar is r into n, means that if you are looking at the states which are labeled by j naught, j naught acting on this state delta n gives you delta into delta n. J naught bar will not act in the same way. J naught bar will have to shift this by so that's the thing. So it'll shift this by this Rn. Okay. So that's what would happen. And so now so we see that we need to impose this on on our states. Okay. So in sort of in addition to the free boson answer that we had before, now we are going to have the partition function on the circle, which is the free boson answer, times this guy which we have here. Okay. Now that is so if you do this, so you're going to get the eta squared again, and you'll have this extra extra pieces, which will give you q to the half delta squared out here, and q bar to the half delta minus Rn squared here. Okay, so that is what we so again, now what you can do is you can try to see if this particular partition function is invariant under modular transformations. Now something very interesting happens. So let's do this. Okay, let's try to focus on this. So if you do this shift, what you can understand that, remember the fact that, Q was 2, sorry, e to the 2 pi I tau, right? So if you do this and plug it back now, so what is going to happen is that you are going to pick up an extra exponential 2 pi I n into delta r minus r squared n over 2. So your partition function is not going to be invariant because of some factor like this. Okay. If you are to demand that your partition function is invariant, this extra factor cannot be there. This particular extra factor can't be there. So that restricts what the form of delta would be. Okay. So now, so you have to, so in if you demand that your partition function is modular invariant, your weights have to be of the form m over r plus r n over 2. So if you do this, you plug this in out here, and you'll see that this just would go away. Where is it? Here. So if you did this, you'd see that your extra factors just drop off. That is going to mean that J naught acting on these states now are going to be given by m over r plus r n over 2. And J naught bar, the sign out here is going to flip, and that is what you're going to get. So you're going to get some states which are going to be happening because this thing, there is winding around. Okay, so once you get back the thing that has happened is that your state out here has some sort of winding number, if you wish. It can wind back. Okay, so it's sort of something like, if you're thinking again of a string, it is sort of, if you could have a closed string which goes like this around. If you're trying to wrap things around, say, a cylinder, it could go around once. That's your usual thing, but it could wrap around it once more and then get identified, or it could do this more more number of times. Maybe let me try and just show you what I mean. So suppose you are doing things not on the plane but on a cylinder. So you have something like this, and you could have some string which winds around just once, and that is fine. But what you could also have is some object which goes around like this, winds it around once, and then sort of comes back, it loops back, or it could do more of such things. Okay, so it could wind sort of n times around it. Okay, and get back. So depending on what how many times this is going to wind around, you're going to get extra modes. So this is these are if n is not equal to 0, these are called sort of winding states. And as I just showed you, these correspond to strings which are winding around n times around this particular circle. So now what happens is your partition function, which is now going to be invariant under your T transformations, will be given by this form. Okay, and that's nice. So this particular thing is T invariant. Trying to prove S invariance is somewhat more involved, but one can actually show that this guy is actually S invariant. Now finally, there is this very interesting feature that if you look at a circle, and if you look at this partition function of this on a of a free boson on a circle of radius r, and if you look at this at a circle of radius 2 over r, then the partition functions are one and the same. Okay, this thing, this thing is what is what is actually called T-duality. This, from the point of view of the string, from the point of view of string theory, if you wish, implies that a closed string, would not be able to distinguish a circle which is of size r or of size r. I mean 2 over r. So that as well mean okay. So another thing that you can see from here is that if these two things are equal, if r is equal to square root of 2, this is sort of like a fixed point of this of this equation. So the fact that a string can't resolve what is r and what is 2 by r, in a sense, gives you the minimal length a string would be able to resolve, and that becomes this a square root of 2. Let's not go much more deep into this, but just from the point of view of what we have done so far, we have said that first we were just looking at the partition function of a free boson, and there we saw that if we were to demand that it has to be modular invariant, we needed to check its transformations under the T transformations and S transformations. The S transformations showed us that the naive thing that we wrote down at first does not work. We had to multiply this square root of this imaginary of tau with that, and by that we could make it invariant. Then we moved on to a circle. When we moved on to a circle, again, so we needed to keep track of the fact that a j naught and j naught bar on these states act in a way which is not the same, and there is this r into n which is going to also appear in when we're looking at the j naught bar, and that essentially means that when we write down the partition function, there is going to be this extra piece here, and we found that this is not invariant under tau goes to tau plus 1. It picks up this extra piece out here. So if we demand that the partition function of a free boson on a circle is modular invariant, what we find is that the spectrum is actually going to is going to have a certain form. Okay, so if this spectrum has to have a certain form, then what do we get? What we get is yeah. So this means that there are going to be states which have windings. If n is not equal to 0, so then there'll be states which will have windings around, and you can write down the T invariant uh, partition function as 6.31. You can also you can also check that this particular thing is S transformation invariant. This is a little more involved, and we will you will get this as homework, I presume. So yes, and at the end of the day, what I also wanted to say is that there is this very interesting property that if you are looking at a circle of radius r, and if you're looking at a circle of radius 2 over r, these two are actually give you the same partition function. This is something which is called T-duality. Okay. Okay, so that was it for bosons on a circle. So yeah, let me get rid of this. Just give me a second. All right. Very good. Now, suppose my circle is r is equal to 2 root k. Square root of 2k. Okay. Then what we are going to do is we're going to start off with some chiral states. Okay. So by this I mean that your L naught acting on these guys will have to be equal to 0. So this means that when you plug it into what we have just seen, it means that M and N have to be related by this number K. So if we're looking at the sector, then we are going to in the sum for the partition function, what we have to do is we have to put M equal to Nk, and we have to put R equal to root 2k. If we do this, our sum takes a nice form, and this is q to the kn squared. Okay, this particular sum over all n is something which is a theta function. This is what a theta function is actually defined by. So the general form. So this is theta function which has an index 0 and k. So you can see the k from here, and the more general form of a theta function is something which has m and k in it. So the number n here actually runs over z plus m over 2k, and you need to sum through all of these guys. Okay, so good. So that is what the general theta function is. If you use this, then your partition function, this is again something, I just wanted to make sure that you get a flavor of this, but yeah, you can work out the math on your own. This is reasonably straightforward. So the partition function that we wrote down earlier can actually be written in terms of these theta functions, the mod squared of them. Okay, and this is similar to this. So there is going to be an eta mod eta squared, and there are going to be these theta functions, and there's going to be a sum here. So that's when you're doing it for all k. Okay. Now, suppose k equal to 1, then the sum here just runs from m equal to 0 to 1. And so the things that you're going to get are theta 0, 1 and theta 1, 1. Okay. So the partition function is going to be given by 1 over eta mod eta squared times theta 0, 1 squared plus theta 1, 1 squared. So this is going to be the case when k equal to 1. Okay. Now we are going to define something called characters. So what are these guys? Characters are of an irreducible representation h1 with hi with highest weight hi is going to be defined as these chi i's of tau, where you are going to trace trace of q to the L naught minus c over 24. Now this trace is not over all states of of the theory, but it's only over those states which are built on top of this particular highest weight state. Okay, so the partition function you remember was a sum over all states. Here this particular thing is going to be the sum over these things which are labeled by hi. So chi I is the character with respect to hi. Okay. Now, if you do the exercise again, then what you're going to see is when you're looking at z at k equal to 1, then you're going to actually get chi I of chi I naught squared plus chi 1 naught squared plus chi 1 1 squared, where chi 1 is just given by this particular this particular function of theta m1 by eta. You could ask me where I'm going with all of this and why I'm saying all of this to you. It's just to show you that in sort of general, what will happen is that you can express the partition function as a sum over, or all of these these characters that we have just defined out here. Okay, so you know, this is again probably a little too much information at the moment, but let me sort of wrap this up by saying that you know, you can find out what the modular transformations. Okay, let me actually probably this is going to be a little heavy, I guess. Okay, so let me stop for now, and let me try to say this a little bit more again next time around. The reason why I was trying to go through this is, if you did it, if you knew what the transformations of these objects were, then you would know what the transformation of these chi's were. I mean, modular transformations, and you could write down partition functions, and you would be able to deduce how you can get modular invariant ones, okay, by looking at the transformations of I mean, modular transformations of chi's, that would say how you can put your left sector and right sector of a I mean, of a CFT together in a modular invariant way. So that is what I wanted to get at. I think at the moment it's a little too much information. So let me maybe get back to this once more next time around, because I think I went pretty fast over what I said in the lecture today, actually. So let me pause for questions, and we will try and revisit this again next time around, just to make sure everybody is on the same page. And then yeah, so we will try. Yeah, so what we are going to be doing is we are going to be taking one extra class next week, that is going to be on Friday the 27th. And so that will make sure that we have I mean, enough number of classes to ride I mean, to sort of wrap this up in a nice way. So next week, guys, we will have 3 lectures, and Friday, when on Friday is fine with you guys?
3 to 4 is fine, I guess.
Is 3 to 4 all right with everybody?
Actually, I
yeah,
have a little problem that time.
okay. So when would it be good for you?
So can we have it in the morning, maybe?
Morning. We could start at 11 if you guys want.
That would be fine.
Is Friday 11 o'clock okay with you guys? All right. If I don't hear anything else, then we will try to put it Friday at 11 o'clock. And yeah, we will try and wrap up the course in that class. I mean, I just have a few more little bits to do, so I will try and wrap things up. So yeah. So if you have any questions, please.
Excuse me, sir.
Yeah.
So I have a meeting, like my thesis meeting at Friday 12. So will we finish it by 12, or should we start a little early, say 10-15 minutes early, so that we finish by 12, just in case it gets extended?
Maybe you are right. Maybe let's aim for something like 10:30 or something like that. Then. Okay. So let's do that. Friday we will start a little earlier. Okay.
Don't we have a class on 30th?
Sorry?
So don't we have a class on 30th of November?
No. So what is going to happen is that I'm going to take make sure that you guys. So 30th is I don't know, is that a holiday or something? I don't know, but we will not. I will not try and keep things for the 30th, because your presentations are going to be on the 1st. Okay, so I don't want to have a lecture on Monday and then you guys speak the next day. So that is what we will do. Is that okay? I mean, it's fine for me to try and take a class on the 30th, but I thought that you guys might not want that. Okay, let me.
Yeah,